to know what an allotrope is, and you really need to know what an allotrope is, because I'm pretty sure it's a test question. They are two or more different molecular forms of the same element in the same physical state. So, same element, same state, but they have different structures, and because they have different structures, they have different properties. So, two sames, two differents. Same element, same state, different structure, different properties. This would be, or an example that we have, are the allotropes of carbon. These three things, diamond, graphite, and buckyball, are all made out of carbon and only carbon. Buckyball is a short name for what it actually is. So all of these are made out of carbon. Now, the two that you know, a diamond and a graphite. Graphite is what you are writing with right now if you're writing in pencil. Okay, we call it pencil lead, but it is not lead at all. It is graphite, and it is made only of carbon. And the diamond is made only of carbon. Yet, these are two very, very different things, aren't they? All right, so the difference is the way that they are bonded together. A diamond has three-dimensional covalent network where it's carbon bonded to carbon, and it forms that covalent network. Much, much stronger than what happens in graphite. Graphite, you have carbon bonded to other carbons, but they're like in sheets. And the sheets are just kind of stacked on top of one another, only held together by intermolecular forces. And now that works out well when you're using a pencil because it leaves part of your pencil or part of that graphite on the paper, although they are easy to break. I always break the pencil, especially out of those mechanical pencils. All right. Again, carbon, only carbon, but because they are bonded differently, they have very different properties. A buckyball is a Buckminster fullerene. It's actually the longer name for that. And it is carbon 60. It is 60 carbons bonded in a sphere. We could not figure out exactly how that structure happened. We had a lot of scientists working on that. And we've gotten a carbon 60 from meteorites, and we were trying to figure out what the structure was. Some scientists were working on this, and one of the scientists just needed to take a break. So he took his lunch break and went out to a park. Now this was over in Great Britain. And the park he happened to go to had a structure on there, and it's just an artistic structure, probably about as big as this building, at least tall. And it kind of reminded me of the Epcot Center. Okay, so it's a round structure. And when he saw that structure in the park, he was like, I wonder if that's how the carbon's bonded. Went back to the lab, and it worked. And so they named it Buckminster fullerene after the architect who designed the building in the park. And that's how it got its name. Now, it doesn't really have a use yet. Again, we have found it from meteorites. We know it does exist in other places other than Earth. They've tried different things. I've seen where they've tried to isolate the HIV virus by surrounding it and putting it into this buckyball, but nothing has necessarily come from that. But they're still trying to find a use for it. All right. Those are your allotropes. You need to know what it is, and you need to know that example. Okay, now we're going to talk about changes of state. A lot of these you already know. And the best advice I have for you is to think about water, all right, when I ask you these. So, going from a solid to a liquid, what is that called? Melting. Good. What about going from a liquid to a solid? Freezing. Okay, and you know it doesn't have to be cold to freeze. Just generally what we associate it with. Okay, this next one is one you may not know, and it is a solid to a gas. This is what dry ice does. It is a form of vaporization, so it is making a vapor, but it has a very specific name. Does anyone know? Sublimation, all right? It sublimes. And I'll try and bring in some dry ice tomorrow, and we'll look at that and watch that solid sublime. It goes directly from solid to the gassy phase, does not enter the liquid phase at all. So it's one of my favorite science courses.
Also, the sublime.
Yeah. evaporation. Again, both of those are forms of vaporization. Now, I say evaporation there because that can happen at any temperature. At boiling, that's when it has to be at a specific temperature. But evaporation, you can go from a liquid to a gas at any temperature, and it's called evaporation. The next one, gas to a liquid. Condensation, good. And then the last one is gas to a solid. This is the opposite of sublimation. And this, again, may not be one that you know, but I'm going to see. Okay. It is called deposition. Basically, the gas deposits a solid. You may have seen this if you have like an old chest freezer at home. It will get caked up with ice crystals over time, and every once in a while you have to empty everything out and defrost the whole thing to make that stuff go away. Because every time you open it, you're introducing water vapor from the air in there. It gets really cold, and it goes directly from a gas to a solid and develops as ice crystals. Some of you, or all of you probably, will be going to college here in either the next year or so. And you're going to get one of those little refrigerators for your little dorm room, and sometimes it even has a little freezer in there, and that freezer is worthless. Let me just tell you, that thing will not freeze anything except itself closed. That is what it will do. And again, every time you open it, water vapor from the air gets in there, and it will deposit it'll go from a gas directly to a solid, and you'll get just this big giant block of ice crystals, and you have to chip through it to try and open up that freezer. It won't make an ice cube. It will make itself an ice cube, but not an ice cube for you to use at all.
That's how ours is. We have one in the bottom basement, and it's just pretty much frozen shut.
Yeah, and it's from deposition. All right. Now, I will tell you, college, you have roommates and things like that. Sometimes you have good ones, sometimes you have bad ones. I had a nice string of bad ones. So, I had, the person I got paired with when I first went to college was a sorority girl. Oh my gosh! And that didn't work out so well. So, I moved into a friend's room because her roommate didn't show up. And I was like, yeah, rooming with a friend, this is awesome. Not awesome. Girls, I will tell you this right now. And I said specifically girls, do not room with a friend when you go to college. They will not be your friend very long. It'll be great for like a few weeks, maybe even a couple of months. And then it will turn sour, and it will be bad. Alright? So you want a nice, clean acquaintance. This does not apply to guys. Guys, they can get mad, and then they solve it, and then things are good. But girls, you know how we hold on to grudges forever, and it just doesn't work out so well. So I moved in with this my friend. She went to class for I'll give her 6 weeks. She went to college for classes for about 6 weeks, and then she just stopped going. And so she just stayed up in the dorm room and smoked cigarettes all day. Now, and her mom was a single mom, and there were 3 kids in college. She was the youngest. She was put on academic probation, came back for the next semester, and she's like, I'm really going to do it this time. I'm going to go to class. And she went 2 weeks and stopped going. And so her mom paid for a year of college. She had nothing to show for it. Nothing. And she was not invited back for the next year. She also, there were lots of other problems. She was also kind of like dirty. Like she just was not very clean with her stuff, and a lot of it was my stuff, so she got my stuff dirty. Like she really did not like to wash dishes, so she would just put dirty dishes in my refrigerator so they wouldn't go bad. She did that over Christmas break, but at Christmas break, when you go home for college, they cut off the power to everything. So not only were the plates nasty, but then when I came back, the entire refrigerator was gross because it had grown stuff from the plates. She was smoking cigarettes and like ashing in some of my Tupperware. And in college, Your Tupperware is what you like. You eat out of that. You store food in that. You cook in that. I mean, that is just that is what you use for everything. And she's ashing her cigarette into it. So I just moved the Tupperware out of the way and moved that ashtray underneath her, and she went, and it was over. I lost it. I was so mad at that point, and I kind of let her have it. She's also ended up being a little bit of a kleptomaniac and would steal stuff. She had a great job at a really cool store you could walk to. It was right across the street from campus. And she would come home and have all this stuff. I was like, I thought you were trying to save up money. She's like, I am. And I was like, how did you get this stuff? And she's like, they gave it to me. I'm like, they did? She's like, yeah, they did. Yeah, they did. She stole it. And then she got tired of working. I know that's a shocker. And instead of getting on the phone and calling up her employer like a big girl, she took her arm and beat it against the table until she had a bruise from her wrist to her elbow. And then made up this lie about how she was attacked on the way to work. Some random person attacked her on the way to work, and that's why she wasn't at work that week. And then she just never went back. And so I got when you go off to college, you get a little 2-drawer filing cabinet. It's not for files. It has a little lock on that, and that's what you put all your stuff if you don't want other people to take. Just saying. Now, how I got my last roommate, this is the one that worked out really well. I went into the student lounge at my college, and I said, yeah, anybody need a roommate for next year? And one girl that I had a class with was like, yep, I do. And I was like, awesome. And that's how I met the last roommate. She was the most sane roommate I had. And she was nice when I was around. We would hang out, and then it's like, oh, gotta go. She's like, bye, have a good time. See you later. And everything was fine. So you want a nice, clean acquaintance, not your friend to bring with. Just my advice, all right? You can try it. Okay, so anyway, deposition. That's what's going to happen on the inside of your college refrigerator, and hopefully nothing else. All right, let's see. All liquids freeze, but at different temperatures. Even antifreeze freezes. It's weird, doesn't it? But all liquids freeze, and some of them freeze at higher temperatures than water. Some of them freeze at much lower temperatures than water. Let's see. Antifreeze. Where does that go? In your car, yeah. Where in your car? Yeah, what part of your engine? In the... Oh, it goes in your radiator. Okay, what does the radiator do? Yeah, I don't know. What does your radiator do?
I don't know.
What is your radiator full of? No. It'll have some of that in there, should cooling in water. Okay? So the water's in there to cool off your engine because moving parts produce a lot of heat, and the radiator has the water in there that moves throughout the engine to cool that, to transfer the heat and cool your engine down so it doesn't overheat. And that's what happens in your car. If it does start to overheat, there's usually a problem with your radiator. Okay, the coolant's not getting to it. It's very, very important that the water in your radiator not freeze. Number one, if it freezes, it could bust open your radiator. And then you're not getting coolant, so your car won't work, and you have a busted radiator. The other one is you could have a block of ice in your radiator. Again, if the water's not moving, it's not cooling off your engine, and your engine's going to overheat. Now, you do not, and so you put antifreeze in there so that it lowers the freezing point so that that water does not freeze. We have different antifreeze here in the south than they do up north because we don't get the really, really low temperatures that they do up there. So they have different grades of antifreeze. Let's see. What's the other thing I was going to say about antifreeze? Okay, yeah, it can freeze. I don't know. I can't remember what it is now, but yeah. So that's how your car works. Oh, I know. If your car starts to overheat and you see that little needle going to H, what do? Pull over right there. There you go. All right. Without, just like she answered that, without thinking, you pull over and stop right then. This is not, oh, I can make it to a gas station, or, oh, I can make it home. No, stop then. Because if you don't, you can really, really hurt your car. All right, beyond whatever the problem is that's causing it to overheat. You're going to make the problem way bigger and way more expensive. All right, so there are your car lessons today. All right.
Stomp it as hard as you can until you see how fast you can.
All right, now phase, uniform composition and properties. I have changes of state there. It sounds very permanent. I really like to call them phase changes because every substance can be a solid, a liquid, or a gas, and it's just a phase that it's going through depending on the conditions. And so it is a much more fluid thing. So you'll probably hear me talk about it more as a phase change rather than changes of state. Oh, sorry about that. Okay, again. We'll try and do this a little bit better. Okay, vapor pressure of a liquid. In a closed system, which is a container with a lid on it, some liquid particles vaporize. These particles collide with the walls of the container and produce a water vapor. So I have a closed container here, which is just a plastic water bottle, and it has some water in there, and then I have this space up here. If I try to squeeze that space, I just can't do it. Why? There's air. Now, is it just air from here? No. What else is it going to be? Water vapor. All right? Because water evaporates. If I were to open this water bottle and leave it open for weeks, the water level would go down because it would be evaporating. There is no difference when I have the lid on there, except it's not going to all go away. But stuff does evaporate. And you know this, if you've accidentally left a water bottle in the car, especially in the summertime, you come back and what do you notice in this little air space above the water? Condensation. All right? So evaporation, an important thing about it is that it only happens at the surface. It's liquids turning into vapor at the surface of the liquid. It can't happen in the middle. In the middle, if it did, it would look like it was boiling. And things don't boil at room temperature, at least with the conditions that we have right now. All right, so evaporation happens from the surface. So some of the particles at the surface gain enough energy, and they escape to that vapor phase. Then they're banging on the walls of the container, and they lose energy and condense back down. At the same rate, another particle is going to evaporate and bang on the pressure. So I got a visual for you there. Let me show you this. Talking about the particles. Here we go. All right, so I have a liquid and a closed system, so I put a stopper in here. And now I have particles at the surface that are going to escape their attractive forces. They move up into here, and they're banging on the walls of the container, and that's what we'll call our vapor pressure. Some of those will lose enough energy, and they will condense back into a liquid. At the same rate, others will be escaping into that vapor phase. Well, it hits a certain point where that rate is standard. Every single time, some are evaporating, and at the same rate, others are condensing, and it sets up this little cycle. And you have a set vapor pressure above a particular liquid. And it has to deal with how strong their attractive forces are. All right. So that's what's going on in a liquid vapor system, and it is equilibrium. And the way that we talk about that is, a little thing here. It's called equilibrium. You have liquid going to vapor, evaporating into vapor, and vapor going into condensation. You see that double-headed arrow? That is equilibrium. And it will establish after a little while. And what happens with equilibrium is you have equal rates. And that's what's equal about equilibrium. Rate of evaporation is equal to the rate of condensation. Now, vapor pressure is measured by a manometer, not a manometer, but that would be handy to have.
Well, I just heard that joke.
Manometer. Okay, but it's manometer. Now that measures specifically vapor pressure, and it's kind of a U-shaped tube, and we deal with the different height of columns, but we don't necessarily deal with that in this class. Now, that measures vapor pressure. What measures atmospheric pressure? Barometer. Barometer measures atmospheric pressure. Manometer measures vapor pressure. So make sure you have those straight. All right, we're going to talk about the kinetic molecular theory and if I add heat to this closed system. So I'm going to add heat to this water bottle. What's going to happen to my rate of evaporation? It's going to increase. Why? Because I have more energy, so the particles will be moving faster, so more of them can escape to that vapor phase. If I have more of them escaping to that vapor phase, am I going to have more or less vapor pressure? More. If you've got more vapor, you have more things banging on the walls of the container. All right, so if you add heat, it increases the vapor pressure because you have more vapor. And I say this in a really long run-on sentence here. So, adding heat increases kinetic energy, which increases the amount of particle able to escape to the vapor phase, which increases evaporation, which increases the concentration of vapor, and that increases the equilibrium vapor pressure. All right, now we're going to talk about volatile liquids. Sounds like something really awesome, and I hate to disappoint because the definition is not as awesome as the word. A volatile liquid is one that evaporates very easily. I have readily on there, but easily. Acetone and alcohol both are volatile liquids. So they evaporate very, very easily. And you know this if anyone has acetone is fingernail polish remover. If you have fingernail polish remover open, or somebody does, you know it as soon as you walk into the room, don't you? Because you can smell it. And the reason you can smell it as soon as you open that cap is that it evaporates very, very easily. And so those scent molecules just go into the air, and that allows you to smell it. What is it about that substance that would make it able to evaporate easily? Good. The type of intermolecular forces that it has. So acetone and alcohol, because they are volatile liquids and evaporate very easily, they must have what kind of attractive force? London dispersion forces, exactly. And that doesn't take a whole lot of energy to break. And the room heat is enough to break those intermolecular forces. Again, this chapter is all about those intermolecular forces. Okay, now we're going to talk about boiling. Now, you may not have, if I have you define, like, what is boiling? Define boiling. Hot. Yeah, but not just hot. How would you define boiling?
Very hot.
Wouldn't it really be when the bubbles happen? Yeah, when the bubbles happen. That's when we talk about boiling, okay? And basically, what's going on with boiling is we have them going from the liquid to the vapor phase, both on the surface of the liquid and inside the liquid. And those bubbles are it turning into vapor. But that's not the Legel-Schmigel definition of boiling. Boiling point is the temperature at which the equilibrium vapor pressure of a liquid equals the atmospheric pressure. So it actually has more to do with pressure than with temperature. Now, when we talk about normal boiling point, and we're going to look at a graph tomorrow or a chart, and they'll ask types of questions like, what is the normal boiling point? So you have to know what that means when they say normal. Normal boiling point is measured at standard pressure, which is 1 atmosphere, or 101.3 kilopascals, or 760 millimeters mercury. So if they say normal, you're looking at standard pressure. Okay, this next little bit, I need some room to draw, so I'm going to do this. Okay, so this next one has to talk about how atmospheric changes here on Earth. So I've got a little globe here. Well, this is going to be a sad one. All right, so there's that. Here's Europe over here. Oop, there's Italy. Okay. And there's Africa. All right. So if and this is the atmosphere that surrounds the Earth. Oh, I did not draw that well. Let me try that again. Okay. You can think of it as a blanket. This is all that, all our nitrogen, oxygen, carbon dioxide, hydrogen that's in our atmosphere surrounding the Earth, and you can think of it as a blanket. And all of this air is pushing down on everything on Earth, but at different rates depending on where you are. If I'm on the beach here in California, I have this much air pushing down on me, so it's quite a bit. Now, if I'm over here at Mount Everest and I'm really excited because I just climbed it, yay, I only have this much air pushing down on me. So at higher elevations, what's going to happen to your atmospheric pressure? It decreases because you have less air pushing down on you. Okay, so you have less pressure at higher elevations. We're at a higher elevation than sea level. So pressure here is less than that standard pressure. Right? Does that make sense? Okay. Let's see. All right, so let me get rid of that drawing. Here. The lower the atmospheric pressure, the lower the boiling point. High elevations have low atmospheric pressure. So, Mount Everest is way up there. It is at a very, very high elevation. They don't have enough oxygen to breathe, and most people who climb it do have to have, or at least non-natives, have to carry oxygen tanks for the top. So that pressure is so low that water doesn't boil at 100 degrees C. It boils at like 70 degrees C. You put your hand in that and not necessarily worry about it. It'd be warm, but it's not, it would be boiling, but it's not 100 degrees C. And when water boils, it gets, let's say it's boiling at 100 degrees C, it will not boil at any higher. No matter how long or how high you turn the heat, it boils at 100 degrees C. So once something hits its boiling point, you can't get it to go any higher. And we'll talk about the reasons why tomorrow, but let's say I'm on top of Mount Everest, and just go with my little scenario here, and I want to have a hard-boiled egg, not a soft-boiled egg. All right? So I'm boiling my egg, but it's boiling at 70 degrees C, not 100 degrees C. What do I have to do? No, I'm not going to eat it raw. Ew. Huh? Let it boil longer. Okay? To compensate for the lack of heat that you're not getting from that boiling water, you actually have to cook it longer. And if you like to bake, they'll be on the back of like cake mixes and things like that, high altitude directions. And that's because you have to adjust your cooking times when you're dealing at higher altitudes, because boiling doesn't happen at the same temperature. Does that make sense? All right, good. Okay, now, the next thing is molar heat of vaporization. I like to make sense of words before I actually show you the definition. Molar means per mole, all right? Not the tooth, but per mole. And heat of vaporization. That's the heat it takes to make a vapor. That is the heat it takes to separate the molecules and break their attractive forces. So it's the amount of heat needed to vaporize 1 mole of a liquid at its boiling point. Now, it is specific, it has to be at the boiling point, and a lot of times I'll go ahead and include that temperature into the problem. It's not that you have to do anything with it, they're just specifying that it is at its boiling point. So we have heat of vaporization of water is 2,260 joules per gram. So to vaporize 1 gram of water, which is 1 milliliter of water, it takes 2,260 joules of heat. Why does it take so much heat? Yeah, why does it take that much energy? Yeah, why? Because hydrogen bonds are strong. It takes that much energy to break those really, really strong attractive forces. So remember, hydrogen bonding is really, really strong, and it takes a lot of heat to break those in order for it to become a vapor. All right. So simple problems. Oh my gosh. You would think I could do a simple problem. Okay. It involves Q equals, and this is your equation, Q equals mHV. This equation is given to you on your reference tables. Q equals mHV. Q is heat, or heat energy, and that is going to be measured in joules. And I know it's weird that Q is heat, but it is, and I think the way they justify it is it's the quantity of heat. Whatever, get used to Q being heat because this will help you out when we get to thermo. M is mass, and that's measured in grams, and then HV is your heat of vaporization. That constant is also given to you, at least for water. So the problem that we have here, how much heat does it take to vaporize 11 grams of water at 373 Kelvin? Well, 373 Kelvin is how much Celsius? 100 degrees C. You just subtract 273. So that is the boiling point of water, and they're just specifying that temperature because it has to be at the boiling point. All right, so it's at the boiling point. It's asked how much heat. So what variable am I looking for here? Q is what I'm looking for because that is heat, and my mass is 11 grams times my heat of vaporization, 2,260 joules per gram. Grams cancel out. All I'm left with are joules. And we need 3 sig figs, so I think it's 24,900 joules. Now, joules pretty small, so generally if it's over 1,000, we go ahead and convert it to kilojoules. How many places do you have to move the decimal to go to kilojoules? From a base unit. 3. So 1, 2, 3, it's 24.9 kilojoules. That's how much heat it takes to convert 11 grams or 11 milliliters of water into vapor. That's quite a bit of heat. All right. Now we're going to talk about freezing and melting. Freezing point is affected by pressure, but not as much as boiling point is. Freezing point is the temperature at which the solid and liquid are in equilibrium at 1 atmosphere of pressure. Freezing and melting occur at the same temperature. Something's freezing point is its melting point, and vice versa. In the wintertime, we're all excited about 32 degrees Fahrenheit because that's when water freezes, but that's also when water melts. They're actually in equilibrium, and it'll be just like that liquid water or liquid vapor system I was talking about with the water bottle. You will have some melting and some freezing, and it'll happen at equal rates. And it sets up a nice little cycle if it just stays at that temperature. Oh my God. We're just not having a good time today. All right. Molar heat of fusion. Now, this one isn't as easy to understand or identify as heat of vaporization. Molar heat of fusion, again, it's per mole, but heat of fusion is the amount of heat it takes to melt 1 mole of a solid. So Heat of fusion is used for melting. Heat of vaporization is used for vaporizing. The formula looks very much the same. Q equals mHF, where HF is the heat of fusion. Now, the heat of fusion of ice is 334 joules per gram. I think about this number often. Generally, when I have dinner, I don't, and this is just me, I don't really drink anything when I'm eating. If I have something there, it's usually I drink that afterwards, and I don't know why. I just don't really drink when I eat. I also never think about drinks for the table, unless like because I make kids do it, unless my parents are coming over, and my parents like to have iced tea. So I have this in my head, and I'm going to make tea for dinner when my parents come and visit. So I always have this. I'm going to make tea when my parents come to visit, but I always forget about it until the end. Well, when you make tea, it's hot, and then so what I do instead of adding water to the tea and just letting it cool down that way, because I don't have that kind of time, I just pretty much fill the ice pitcher up with ice, or the tea pitcher up with ice, and then pour the hot tea on top of that, and then I start stirring, and I'm like, okay, ice, absorb that 334 joules of heat. Because here, this might blow your mind, Ellie, won't be wait for this. You don't add, ice does not make your drink cold. Your drink makes your ice warm. There is no such thing as adding cold. It's only the absence or the addition or removal of heat. There's no such thing as adding cold. What you do when you put ice in a drink is that drink starts to melt your ice, and the ice absorbs the heat. It uses that to break attractive forces, and that's why your drink goes down in temperature when you have ice. Isn't that weird? You won't look at a glass of iced tea the same way. All right, this works pretty much the same way as the others. Q equals mHF, so how much heat energy is absorbed when 16.3 grams of ice melts. You have to know, and this is the only problem here, because I give you both formulas, I give you the constants. You have to know which one we're using. Melting we use, heat of fusion. All right, so Q is heat, and that's what we're looking for here. Q equals mHF. My mass is 16.3 grams, times my heat of fusion for water is 334 joules per gram. Grams cancel out. All I'm left with are joules, and I think you need 3 sig figs, so that's 5440 joules. But again, if it's over 1,000, we generally change it to kilojoules. So how many kilojoules is that? 5.44 kilojoules.